Bismillah, hello everyone. Welcome to the final presentation of our graduation project. Let me start by introducing our team members. Our team consists of 4 members. Professor Aydin Direk as the team advisor and 3 mechatronics engineering students. Abdelmuti Diab, Abdullah Alloush, and Ahmed Ajam. So, as a reminder, the problem we are trying to solve is simply that many library assistants nowadays waste their time, do repetitive tasks, perform tasks that do not require any creativity. This is surely labor intensive. So, we wanted to make a robot that could help lessen, if not eliminate, this problem. Now, I will take you through our implementation progress plan, which followed an engineering design compatible flow. Let's dive in. First, theoretical design. We began with theoretical design phase during the MSD course in the previous semester. This laid the foundation for our project. Second, software algorithm implementation. Once the theoretical design was in place, we focused on finding, improving, and implementing the software algorithm for path planning. Thirdly, mechanical system. Building upon the software algorithm, we shifted our attention to the mechanical system. This involved assembling the physical components of the robot, ensuring a sturdy and functional structure. Fourth, electrical system. With the mechanical system in place, we proceeded to integrate and wire the electrical components. This included power supply, sensors, and any necessary circuitry. Fifth, control systems. The next step involved implementing the control system. We designed and implemented a control algorithm to regulate the robot's movement and ensure precise navigation along the desired path. 6. Testing and validation. Finally, we conducted rigorous testing and validation processes. This allowed us to assess the performance and functionality of our robot, making any necessary adjustments to achieve optimal results. By following this well-structured plan, we were able to effectively progress from the theoretical design phase to a fully functional robot, ready for deployment. As I mentioned, we began our progress by evaluating the outcomes of the MSD theoretical design. After careful considerations, we made the decision to enhance the technical requirements of the robot, specifically focusing on maximizing its speed and acceleration to improve its time efficiency. These modifications necessitated a change in the motor specifications to align with the new technical requirements. In this slide, you can find the updated parameters alongside their corresponding original values. In the upcoming slides, we will dive into the implementation process of our design mechanical system. We will showcase the step-by-step progression, beginning with the assembly of individual components and ending with the completion of the final structure. As you can see in the displayed images, we have acquired various mechanical components such as sigma profiles, connectors, plexiglass plates, wheels, motors, and much more. These components will collectively form the fundamental mechanical structure of our robot and will be seamlessly integrated to create the overall mechanical framework. During the initial phase, our focus was on preparing the essential corner connectors to ensure a solid foundation for the robot structure. Next, we seamlessly connected the sigma profiles, shaping them into a sturdy box-shaped framework. To enclose the sides of the box, we processed the edges of the plexiglass plates so that they snugly fit in the corners. This combination of sigma profiles, corner connectors, and plexiglass plates forms the resilient and durable mechanical chassis of our robot. Moving forward, our attention turned into the integration of wheels with the motors, followed by securely attaching the motors to the robot's chassis. L brackets emerge as the key components responsible for facilitating the carry of mechanical load from the motor and enabling the seamless transmission of mechanical motion. These robust L brackets played a vital role in maintaining stability and ensuring the efficient functioning of our robust mechanical system. Given our limited budget, we embraced a do-it-yourself approach to design the upper plate of our robot. By repurposing a plastic tray as the foundation and utilizing containers originally intended for dry food storage, we created a cost-effective solution for holding books. To enhance its visual appeal, we applied black spray paint and unified the tray and containers together. This resourceful approach not only allowed us to repurpose available materials, but also resulted in a practical and visually captivating design. We then securely attached the upper plate to the main chassis of our robot, completing the integration of the mechanical system. With this step, our robot's mechanical framework is fully prepared to fulfill its intended functionality, enabling the efficient transportation and retrieval of books. This seamless integration sets the stage for the successful interaction of our project's subsystems. On this slide, we have the original CAD design model showcased on the left image, and on the right image we can see the final form of our robot's mechanical structure. Notice that certain features have been modified in response to prototyping simplicity and budget limitations.
In the upcoming slides, I will be talking about how we put together the electrical and electronic system. We will show you all the process, starting with individual components and finishing with the final circuit. In this slide, you can see that we have several electronic components for our robot, such as the Raspberry Pi, DC brushed motors, and motor drivers, and more. These components will work together to create the electronic and controlling system of our robot. In the electronic and electrical wiring implementation, we began by determining the power sources for our robot. We have two LiPo batteries. One is connected to a voltage regulator to provide the 5 voltage power required for the components, while the other battery is for powering the motors. Next, we started to connect the other elements to the Raspberry, following the assigned pins as specified in the table. This ensured that we wired correctly and the components were connected to the Raspberry Pi. To manage power and ensuring safety in our robot, we have included a wattmeter. This device allows us to monitor the current and power consumption of the components, ensuring efficient and safe operation. For charging the batteries, we have a specialized LiPo battery charging plate to ensure the batteries are safely and properly charged. On this slide, we have the original electronic diagram on the left image, and on the right image, we can see the final result of our robot's electronics circuits. Our robot has some important safety features. One of them is an ultrasonic sensor that helps avoiding collision with moving objects by detecting nearby obstacles in real time. Another useful feature is an RGB LED which displays different colors to show the robot's current state. This helps customers and library assistants know whether the robot is moving or waiting for the items to be placed. For the communication and programming of Raspberry Pi, we used SSH and utilized its built-in Wi-Fi model.
In the upcoming slides, we will explore how we put together the control system we designed. We will walk you through the step-by-step process, starting with theoretical concepts and ending with physical implementation. The control system plays a crucial role in integrating the mechanical and electronic subsystems together, ensuring their seamless coordination and synchronization. We will delve into the details of how the control system combines these subsystems, highlighting its significance in the overall functionality of our robotic system. For our library assistant robot prototype, we have adopted the differential drive steering approach in the designing process. The differential drive method offered simplicity and flexibility, making it an ideal choice for our robot. By independently controlling the rear wheel motors and adjusting their speeds, we were able to achieve various motions such as turning, moving forward, and moving backward. On the current slide, you can observe the forward kinematics matrix, which displays the robot's weld frame coordinates and heading based on specific motor speeds. Additionally, we have utilized inverse kinematics matrices in the control subsystem to calculate the required motor speeds to achieve desired weld frame coordinates and headings. These matrices play a crucial role in achieving precise and accurate movement control. The wheel encoders serve as a vital component in our robot, enabling us to obtain essential data for accurately determining the robot's current coordinates and headings. By leveraging the readings from the encoders, our code continually updates the coordinates and heading of the robot with each iteration. This dynamic process is facilitated by the equations displayed on the slide, which allow us to translate the encoder readings into meaningful and actionable information regarding the robot's position and orientation. As we are utilizing a digital controller, it was necessary to convert the continuous model of the PID controller into a discrete domain. This adaptation involved replacing the continuous terms of the PID controller with their corresponding numerical approximations. In this slide, we present a comprehensive overview of the discretization process. By the end of this process, we obtain a discrete model of the PID controller capable of effectively controlling any desired physical quantity, let's say U of I. The control of the robot's angular velocity plays a pivotal role in our project. Given the desired coordinates, the robot performs calculations to determine the necessary heading and displacement required to reach those coordinates. This information is then passed to the angular PID controller, which monitors the error between the current heading of the robot, as obtained from the encoders of course, and the desired heading. By leveraging carefully tuned PID parameters, the angular PID controller adjusts the robot's angular velocity accordingly, ensuring precise control and alignment with the desired path. To highlight the significance of fine-tuning the PID parameters, we conducted numerous experiments to achieve optimal results with a desirable dynamic response. Here in the first video, we will observe the angular control attempting a 45-degree turn without fine-tuned parameters. Let's see what happens. Yes, while in the second video, the second video itself demonstrates the angular control with fine-tuned PID parameters, also aiming for a 45-degree turn. As you have seen, the improved accuracy and precision in the second case are evident, showcasing the importance of meticulous parameter adjustment in achieving desired outcomes. In our kinematic control approach, the robot doesn't account for residual momentum when using constant linear velocities and energy cutoff braking. To address this, we implemented an additional PID controller to govern the linear velocity of the robot. This linear controller continuously assesses the difference between the current position of the robot and the desired coordinates. As the robot approaches the target location, the linear controller gradually reduces the linear velocity. This gradual deceleration mitigates residual momentum, leading to improved accuracy and overall precision in the robot's movement. Just as we emphasized the significance of fine-tuning the PID controller for angular velocity control, we also conducted a series of experiments to highlight the importance of a finely tuned PID controller for linear velocity control. In the first video, the robot is observed maintaining a constant linear speed while attempting to achieve a direct displacement of 50 centimeters. Let's see what happens. Okay. Now, in the second video, the robot is equipped with a finely tuned PID controller for linear velocity control, aiming to accomplish the same 50 centimeter displacement. As we have seen, the results obtained from the second case clearly outperform those of the first, underscoring the superiority of employing a well-optimized PID controller for precise and accurate control of the robot's linear velocity. Now, allow me to remind you of our algorithm. The main goal of our robot is to visit multiple bookshelves to deliver back the carried books. So we have worked on developing an algorithm that provides the robot with a near optimal visiting configuration of a given set of goal nodes. The image shown in this slide represents a 3D map of a library with multiple obstacles including bookshelves, tables, chairs, etc. To deliver back a number of books to their original shelves, there exists numerous visiting configurations. They are shown in the map. Our algorithm will try to pick the best of them. Our algorithm necessitates a 2D top view map of the workspace. This map has to be in grayscale format in which the obstacles are represented by black color and the available passages are represented by white color. The implementation of our algorithm is the crucial part of acquiring a path, which is the first step for our robot to work. In this video, we present a visual representation of the map of the library that our robot will navigate. The map was meticulously created with a scale of 1 pixel representing 1 centimeter. The available passages are depicted in white, while the obstacles are represented by black areas. To establish the initial and goal locations for book delivery, we manually marked the corresponding nodes within the library map. Utilizing our algorithm, we successfully generated a sequence of ordered goal nodes and a path that skillfully avoids the obstacles present in the map. After acquiring the path coordinates, we upload it to the robot and run the code. As you will see in the video, the robot fulfills its objectives of helping the library assistant and delivering books to their desired locations. That was our graduation project, and thank you for listening.